Hello and welcome to the Unit 7 podcast on section 15.3. Today we're going to be discussing colligative properties of solutions. I'm Mr. Sakaguchi,
I am Mr. Lin.
and let's start. What are colligative properties? These are physical properties of solutions that are affected by the number of particles but not the identity of the particles themselves.
So when we're talking about physical properties, we're talking about things like boiling point and freezing point.
The only thing that matters with respect to the solute particles themselves is how many will actually form in solution. If you remember back in section 1, we talked about the difference between non-electrolytes or molecular compounds versus ionic ones, which are electrolytes. With respect to non-electrolytes, the number of molecules is basically equal to the number of dissolved particles. But because electrolytes, which are almost always ionic compounds, dissociate, the number of dissolved particles will not be equal to the number of formula units. For instance, with respect to solid, as it dissolves, you get 2 particles per formula unit.
So an example of a non-electrolyte doing this would be like sugar, and then you would just get a 1-to-1. The sugar molecule doesn't break apart. Whereas with the salt particle, you get a 2-to-1. This is NaCl, so it's a 2-to-1. Versus there are other salts, you might have 3 particles for every salt molecule, and so on.
Yeah, so for ionic compounds, the number of dissolved particles will be equal to the total number of ions that the formula unit will separate into.
And you'll wind up multiplying.
And we'll show why it matters in a little bit.
Right.
One of the colligative properties of solutions is vapor pressure. Vapor pressure basically is the pressure exerted in a closed container by liquid as it evaporates in a closed system.
So as the liquid evaporates, it's going to cause a gas to form on its top layer and push up on the top of the container, which will push back down on the liquid.
It's an equilibrium state, so what happens here is initially when you first cap the system, there's no liquid particles in solution yet. But what ends up happening is this empty space slowly gets filled up with liquid particles that have evaporated. And then you eventually get to the point where some of those gas particles will begin to condense back into liquid. And eventually you get to the point where the amount of evaporation is equal to the amount of condensation. That's where we begin to measure vapor pressures.
And a real-world example of you experiencing this, if you've ever been in an indoor pool, you'll also notice that the space feels kind of stuffy. That's because of vapor pressure.
And also boiling points for liquids is also a situation where the vapor pressure is equal to
The atmospheric pressure.
the atmospheric pressure. That's right. What happens is when we add solute particles to the liquid, it lowers the vapor pressure.
The reason it does this is because now that the solute particles are mixed in there, it's blocking off the top layer, or it's blocking part of the top layer that the solvent particles would normally evaporate with. And now, since some of that space is taken up, there's fewer solvent particles floating off and causing vapor pressure.
Yeah, so because there's fewer particles in the gaseous state, that's why the vapor pressure is lower. A way to kind of measure this under a series of pressures and temperatures is something known as a phase diagram. And every phase diagram basically is shaped like this to a certain degree. You'll basically be broken up into 3 little areas. The solid area will be here, the liquid's in the middle, and the gas represents the bottom part. Depending upon, and there's these lines. These are lines that basically represent transition areas between different states of matter.
And this is usually, as you can see from the axes on the graph, this is represented by how much pressure there is and then the temperature as well. So depending on the pressure and the temperature, water, for instance, would boil at different temperatures. So high elevations, where the pressure is less, winds up having a higher boiling point.
Right, and notice the transition areas. So most of you know what melting and freezing are. Sublimation is going from solid to gas. Deposition is going from gas directly to solid. And then we can have vaporation and condensation as well. These lines represent equilibrium states between different states of matter. One point to note is the triple point. This is the pressure and temperature where all 3 states are in equilibrium with each other. There's also the critical point, and this is the point where no matter how high you crank the pressure up or temperature up, it'll remain a gas.
A minor correction to what I said earlier. I said high elevation. I meant lower elevation. That's where you get the higher pressures.
Oh, lower elevation, higher pressure. That's
Yeah.
right. And then here's our same phase diagram, and what you see in blue is what happens when you add solute particles.
So now that we have our solution, you can see that our lines for the equilibriums have shifted. For instance, when we transition between gas to liquid, we know this as boiling, for instance. Well, now the boiling temperature has moved. Okay, it's lowered due to the different vapor pressure.
Well, the boiling point's actually higher.
Sorry.
Because remember, this is the temperature.
Oh, right.
So it goes from here to here.
Yeah, it goes.
For
It's
instance.
increased.
And then if you look at the freezing point, notice that it goes from.
It's
It's
lowered
lowered as you go from here to here.
as you transition from left to right.
Yeah. Okay. Okay, so boiling point elevation. Now, it's not enough just to know that the boiling point increases. We can actually quantify how much the boiling point goes up. And remember, because the reason why the boiling point goes up is because of the lower vapor pressure. So because of the lower vapor pressure, it takes a greater amount of energy to get to the atmospheric pressure. We can quantify the change in boiling point by using this here. Kb is the molal boiling constant. This is based on the solvent.
So that will be on a chart that's given to you, or it's going to be given you directly in the problem. So it's nothing that you have to memorize or calculate for. It's just a constant for that substance.
For the solvent.
Sorry, right.
For the solvent.
The
M is the molality, which you may or may not have to calculate, and I is the Van Hoff factor. The I represents the number of particles that the solute will break down into. And then we would add this to the boiling point of the pure liquid. Right. For freezing points, basically the same kind of idea. At the freezing point, the particles don't have enough kinetic energy to slow down enough, so you requires the removal of more energy, which requires you to lower the temperature. Again, we can quantify the change in freezing. It's basically the exact same equation as change in boiling. There's a molal freezing constant based upon the solvent, and again, we would need the molality.
Not to be confused with the molarity. So we're doing molality. This is with the kilograms of solvent. Another thing to understand, freezing point depression is not related to vapor pressure. The reason you require a colder temperature is because now you have these solute particles getting in the way of your solvent forming up into an orderly fashion for the crystalline, usually a crystalline arrangement.
And remember, I is the Van Hoff factor again, so the number of particles the solute breaks down into when it forms a solution again will matter here. And this one we would subtract from the freezing point of the pure liquid. Okay, so how will we do this? We'd find the Kb. Again, this is a constant we would look up or would be given to you. We might have to calculate molality, so you have to look at the previous stuff from before. Is the solute ionic? This will help us figure out the Van Hoff factor, or what I is. If the solute is not ionic, I is automatically equal to 1. If it's yes, then we have to figure out how many particles the solute dissociates into. So for instance, if I have sulfuric acid, it's 2 H plus ions and 1 sulfate ion. So the Van Hoff factor would be a total of 3.
So your acid here is breaking into 3 parts, and you have to multiply it.
So then we would substitute our numbers for our variables, and we'd solve for delta TB. And they would add this to the normal boiling point to find the new boiling point of the solution.
Right.
Freezing point.
Same idea. Okay. The KF is given, or will be given to you on a chart or in the problem. And then again, you're using just molality, and you're going to check if the solute is ionic or not. Again, if it's not ionic, your Van Hoff factor is just 1. And then if it is, then you're going to have to multiply it by how many ions it breaks apart into. Then you just substitute all the numbers into the equation and solve. And then since this is called freezing point depression, you're going to subtract it from your normal freezing temperature.
Mm-hmm. And the last thing we're going to talk about is osmosis and osmotic pressure. I know most of you are probably familiar with this with respect to cells. Osmosis is diffusion of a solvent particles across a semipermeable membrane from high to low concentration.
Just understand that the greater the concentration of a solution, then the greater the osmotic pressure.
Yeah, and we can, so an osmotic pressure basically represents pressure necessary to prevent osmosis. And we can measure that, but we're not going to actually quantify it here. Just know what that is. And I think that's it.
Yep.